All right, everybody, welcome back to Chapter 5, Bivariate Data Analysis. Basically taking two numeric pieces of data and graphing them against each other on the x and y axis, okay? In this first section, we're going to study what's known as correlation, which more or less is going to measure the relationship between two variables. Okay, so let's take a look at the reading here. In Chapter 5, we'll study bivariate data, which deals with looking at how related two variables are to one another, specifically numerical variables. For example, is there a relationship between a person's height and their weight? We could get a bunch of people, we could ask them for their height in inches, their weight in pounds, and then we could plot those points and see if there's some sort of relationship. Is there a relationship between how far a person drives a car and the amount of fuel left in the tank? I would think so. Is there a relationship between someone's height and, say, their college GPA? Probably not. For some bivariate data, two variable data, the variables tend to be quite related, while in others, not so much. This chapter will discuss methods used to mathematically determine how related two variables are to one another. Okay, the first thing we look at are scatter plots. And pause it if you need to write the notes down, but a scatter plot is a graph in which the values of the two variables are plotted along the x and y axis. The pattern of points reveals the potential correlation between these variables. Okay, so let's talk more about this. Pearson's correlation coefficient R. Okay, lowercase r is the notation we use to represent what's called the correlation coefficient. And this is a measure of the strength of a linear relationship between two variables. If we look at a scatter plot, how good of a job do these dots do at basically forming a line? Now we have some illustrations down below here, okay? These are 5 different example scatter plots for whatever data, okay? The idea here is just to get a sense, okay, this is what a scatter plot looks like. And looking over the information at the top, we're going to be talking about positive linear relationships, negative linear relationships, perhaps no real linear relationship, or what we call curved relationships in this unit. Focus today is mostly going to be on linear stuff. If you notice, it says A and B both have positive linear relationships. That's because the dots more or less tend to form a line. It's not a perfect line. Part A is pretty close to a line. Part B maybe a little less close than part A. But both of these basically form lines with positive slopes. Okay, if the slope is positive, the relationship is positive. And that's what's meant by positive linear relationships. Okay, if we were to kind of eyeball some line in here that does a good job of modeling the data, this would have a positive slope, as would this one. Notice that C says we have a negative linear relationship. It's not quite as strong a linear relationship as A or even B, because the dots tend to be a little more spread out. But we can see with a little bit of effort that if we were to try to draw some line in here to model the data, it would certainly have a negative slope. So that's what's meant by a negative linear relationship. It really comes down to the slope. Now in example D, we basically have dots all over the place. It's really hard to try and imagine one line that does a good job of modeling the data. Does that do it? I don't know. Arguably, does that do it? Not really. There's no one good line that models the data. And notice that there's no real slope. Okay? This is not linear. And this one, a portion of it looks partially linear, like maybe right there. But in reality, this thing seems to be a little more curved. So when it comes to bivariate data, the first thing we typically do is just look at the scatter plot to get a sense of whether we have a positive relationship, a negative relationship, or perhaps some nonlinear relationship. Okay, and we'll see how we're going to calculate these in just a moment. Okay, so again, the sample correlation coefficient, that's our guy R, also known as Pearson's correlation coefficient. Okay. Lowercase r is the notation. The sample correlation coefficient measures the strength of a linear relationship between numerical variables, two numerical variables. The correlation coefficient is calculated using z-scores. Consider replacing each x value by the corresponding z-score, z sub x. That's done by subtracting the actual x value from the average and then dividing by the standard deviation of that x value, of the x values. And similarly, imagine replacing each y value with its z-score. Notice that x values that are larger than x bar will have positive z-scores, and those smaller than x bar will have negative z-scores. Also, y values larger than y bar, average y, will have positive z-scores. Those smaller than the average y will have negative z-scores. The value of the correlation coefficient is based on the sum of the products of the z-scores for x and z-scores for y for each observation in the bivariate data set. This can be written as the summation of zx times zy. Now let me explain this a little further in detail for you, okay? Suppose we have some scatter plot, okay? I'm just going to kind of eyeball some scatter plot here, just making something up. You know, maybe we have points that kind of form this sort of thing here. So this would be a scatter plot with a negative linear correlation, okay? To show you how these z-scores come into play, this is how it works. Now, I'm going to approximate the average x value. You'll notice like right about here is my lowest x and up here is my highest x. So right about here, I'm going to call that the average x value, and I'm going to notate that with an x bar, okay? What I'm going to do is just kind of draw this vertical line here separating the left half and the right half, okay? Any dots to the left of x bar are x values that are lower than x bar. So these are all going to have negative z-scores. All these that are larger than x bar to the right of it are individual data points that are bigger than average x. These will have positive z-scores for x. Now let's talk about y. As we see from the dots, the lowest y is right about here. The highest y is up here. I'm going to call this the average y. And again, I'm going to do something similar. I'm going to draw a horizontal line here through the average y. Any data up above this is going to have a y value that's bigger than average. So these are all going to have positive z-scores for y, whereas these dots below average y are less than the average y value, and these will have z-scores that are negative for y. Okay, so basically in each, I'm going to call these kind of like 4 quadrants here, and we're just going to kind of notate what the z-scores would be for x and y. Okay, so up above, let's talk about x. To the right of x, these are z-scores that are positive. So here I would have the z-score for x that's greater than 0. Here I would have a z-score for x greater than 0. To the left of x bar, these are below the average x. These are going to have negative z-scores for x. So z-score for x is negative in this region, as it would be over here. Similarly, let's do the same for y. So here's the horizontal line at average y. Above average y, these are y values bigger than average, positive z-scores for y in these two regions. So here the z-score for y is positive, and here the z-score for y is positive. And then conversely, down below, these dots all have y values less than average y, and therefore any dots in these two regions would have z-scores that are negative for y. So the z-score for y would be negative in these regions. Now, it comes down to the sum of the products of these z-scores, okay? That's what this means. We're taking the sum of all the products. We're going to multiply all these zx, zy together. Zx1 times zx2. Let's call this our first point. So like zx1 would be negative because it's less than the average x, but zy sub 1 would be positive because it's above the average for y, okay? So in any event, like make sense out of what's happening with these products. I mean, the bulk of the dots I drew are in these regions. Well, notice in these regions here, x and y have opposite signed z-scores. What's going to happen if you actually multiply these together, a negative times a positive? You're going to get a negative number back. Down in this region, it's the same idea. If the z-scores for x are positive and those for y are negative, when I multiply these values together, a positive times a negative is going to come back negative. So what you're going to end up seeing is that, you know, when the data tend to go down and to the right, we typically have negative r values because these products come back negative and we add a bunch of negative numbers together. If, on the other hand, the dots were basically going up and to the right, we'd have a bunch of positive products of z-scores, two positives multiplied as positive, two negatives multiplied as positive. And so when the dots tend to go up and to the right with a positive slope, you're going to notice you're going to have a positive r value, okay? The formula for computing R is actually given by this. R is equal to the summation is I goes from 1 to n of the product z x sub I, z y sub I, all divided by n minus 1. Okay, and I'll show you an example how we can use this to actually compute an R value in a moment, and then we'll go from there. Okay, but this is the gist. This is the idea with the products of the z-scores dictating whether this thing comes back positive or negative. Now, some properties of the number R. The value of R is always a number between -1 and +1 inclusive. That means it can equal -1 or it could even equal +1. The only time we would ever get an R value less than -1 or greater than +1 is when we are doing this sort of math by hand and we are rounding values. Sometimes it'll come back outside of -1 and 1, but that's only due to rounding. Realistically, it should always be a number between -1 and 1. Now, a value near the upper limit of +1 indicates a strong positive linear relationship. In fact, an R value of 1 means that all of the points fall on a straight line. A value of R that's close to -1 suggests a strong negative linear relationship. As one value goes up, the other value will go down. Okay, so values close to plus or -1 indicate the strength of the relationship. Okay, the figure below shows a useful way to describe the strength of a relationship based on the value of R. It may be surprising that the value of R as small as -0.5 or as large as +0.5 is still in the weak category. We will understand why a little bit later when we talk about this thing called the coefficient of determination, which is a couple lessons away. But in general, here's how what we call R, okay? If R is 0, there's really no correlation. We basically have dots that are kind of like all over the place, something like this perhaps, okay? All right, so in terms of the positive side, 0 to 0.5 is a weak correlation. Greater than 0.5 to 0.8 is what we call a moderate relationship or correlation. And then an R value from above 0.8 up to 1 is considered a strong positive linear relationship. And then the opposite going back. Here we're in the weak negative linear relationship area, moderate negative linear relationship, and a very strong negative linear relationship. So if there's a strong positive relationship, it just means as one variable goes up, so does the other. And they do so pretty consistently. Negative, as one variable goes up, the other variable goes down. Sort of like, the amount of fuel you have in your tank after driving X number of miles. The more you drive, the lower the amount of fuel in your tank. Okay? A correlation coefficient of R equals 1 occurs only when all the points in the scatter plot of the data lie exactly on a straight line that slopes upward. Similarly, R equals -1 only when all the points lie exactly on a downward sloping line. R equals 1 or -1 indicates a perfect linear relationship between X and Y in our sample data. Number 3, the value of R is a measure of the extent to which X and Y are linearly related. R measures the extent to which the points in the scatter plot fall close to a straight line. Okay, so R is very much about how well do the data form a line. A value of R close to 0 does not necessarily mean there is no relationship between X and Y. It just means that it's probably not a strong linear relationship. Okay, it is possible that there could be a strong relationship that's not linear, such as a curved relationship. The value of R does not depend on the unit of measurement for either variable. For example, if X is height, the corresponding z-score is the same whether height is expressed in inches, meters, or miles, and the value of the correlation coefficient will not be affected. The correlation coefficient measures the inherent strength of the linear relationship between the two numerical variables. And number 5, the value of R does not depend on which of the two variables is considered X. This means we can actually flip the X and Y pairs and we will get back the same value of R either way. Okay, typically X is what's known as the independent variable, Y is the dependent variable. We could have a bunch of points like 1, 3, 2, 7, and 5, 10, and I could compute the value of R with that. Then I could flip these coordinates around, 3, 1, 7, 2, 10, 5, okay? And it would have the same R value. That's what number 5 is saying. So it really doesn't matter what you're calling x or y, typically speaking, when it comes to coming up with the value of r. Now, one thing the text makes a big deal out of that I'm just going to reiterate is that correlation does not mean causation. An r value close to plus or minus 1 means a strong linear correlation or relationship exists. But we need to be careful not to say that one thing causes the other to happen, because like with other things in this course, when we're just looking at these two variables, we're not accounting for potential confounding variables, okay? So we really can never say one thing causes something else to happen, even if there's a very strong relationship. We just say that there's a strong linear relationship between the two, okay? Now, let me show you how this works, okay? I kind of got this set up, the first one to do by hand, just to kind of show you how this actually works, okay? So for the data below, I said let x equal the distance a person lives from work rounded to the nearest mile, and let y equal the amount of time it takes to get to work rounded to the nearest minute, okay? And I have a sample of 5 employees. We're going to sketch the scatter plot and then compute the value of r to the nearest hundredth. So basically we have one person who lives basically very close to work, less than a half a mile away, and it takes them about a minute to get to work. Person lives 2 miles away, it takes about 5 minutes, 4 miles, 9 minutes, so on and so forth, okay? Now here's the formula, okay, which again, just kind of, what does this whole thing represent? Well, if I sub 1 in, this is the sum of all this stuff. So if I sub 1 in for I first, my first z-score for x times my first z-score for y, plus my second z-score for x times my second z-score for y, until I get to my last one, okay? And in this case, there's going to be 5 of them. Here, n is 5 because we have 5 pieces of data, 5 pieces of bivariate data, 5 coordinates, if you will, okay? So basically what we need to do is, if we're going to do this by hand, we need to make a table that's going to allow us to compute the z-scores for x and y and their product, okay? So what you see in my table is basically, look, to get to the z-scores, we need to do some work. We got each x value. And I'm going to need to get the average x, so I put that column next. Then I find their difference and I square them. Then, using the sum of this column coupled with the standard deviation for x, I can then, after this I can get the standard deviation for x, which I already took a moment to do ahead of time. And then, once I know all these differences with the standard deviation, I can come up with all of the z-scores for x, and I can repeat for y. Here's y, get the average y, subtract them, divide each of these by the standard deviation, and then I get this. So in fact, I'm not even going to need this because I already have standard deviation and standard deviation for y. So these two columns I'm actually going to block out. We're not going to need that. We would need these if I was computing standard deviation by hand, but I went a little ahead and did that, okay? So let me do this, and I'm just going to clean it up a little bit here. You'll see. Just a sec. I'll do this. Slide these together a little better here. Okay, and we'll do this for our table. And don't worry, this is just kind of a one-time thing to show you how this works. And I'm missing the most important column. I actually need to take the products of my z-scores for x and y. So here's how it works by hand, okay? So look, I already went ahead and found the average of these 5 data points. Add and divide by 5, or use your calculator to do a stat, one variable stats. Okay. And now if I subtract each x minus average, 0 minus 4, 2 minus 4, 4 minus 4, 6 minus 4, 8 minus 4. Okay? And now what I'm going to do is I'm going to take each of these values and divide it by the standard deviation to come up with my z-scores. So if I was to do negative 4 over 3.16, I'm basically getting negative 1.27, and I'm going to round to 2 places. Negative 2 divided by 3.16 is about negative 0.63. 0 divided by anything is 0. Positive 2 over 316 would then be positive 0.63. Positive 4 divided by 3.16 would be positive 1.27. So those are the z-scores for x. Now I can repeat with y. So for y, I already got the average to be 10. You can add and divide by 5, and you should get that as well. I'm going to do y minus y bar, 1 minus 10, 5 minus 10, 9 minus 10, 15 minus 10, and 20 minus 10. So once again, I'm going to take each of these 5 numbers and divide by the standard deviation of y to get the z-score. So negative 9 over 7.62 is about negative 1.18. Negative 5 over 7.62 is about negative 0.66. Negative 1 divided by 7.62, negative 0.13. 5 over 7.62 is positive 0.66. And 10 over 7.62 is 1.31. And remember, what this means is that the number the number 20 in our data is 1.31 standard deviations above the mean. Okay, let's try not to forget what that stuff means. All right, but now what I'm going to do is now I'm going to take the products of my z-scores. So these I'm going to multiply together. And a negative times a negative should be a positive. And again, I just rounded 2 places here. I get about 1.50, we'll call that. Now I'll multiply these 2 together. And we get about 0.42. Now I'll multiply these next ones together. That's easy. That'll just be 0. Now I'll multiply those guys together. And that's going to be, again, 0.42 by the looks of it. And finally, these last 2. And that's going to be 1.66. And I'll try to write with a pen instead of a highlighter here. 1.66. Okay, so this represents the products of our z-scores. And now what we want to do is we want to find the sum of that. That's what that summation symbol means. So I'm just going to put a summation symbol down at the bottom here. And if we add those together, 1.5 plus 0.2 plus 4.2 plus 1.66, and I am getting the number 4. Okay? And so now to compute the R value, basically R is going to be that sum, okay, this guy right here, divided by n minus 1. And we get an R value of basically 1, which is indicative that these dots basically form a straight line. Now what didn't we do? We didn't do the scatter plot. So let's quickly do that. I'm just going to get this out of the way here. And we'll look at our scatter plot. And I'll try to space this neatly. And let's see, I'll count by 5s here. I got to get up to 20. We got 0, 1, 2, 5, 4, 9, 6, 15, and 8, 20. And look, it's not going to be a perfect straight line, but it's pretty darn close, which is why we got it. And notice it's going up and to the right. So we have a very strong, positive, linear correlation here. And again, the only reason this worked out to 1 is because I did a little bit of rounding here. It's not exactly a perfect line, okay, but it's pretty darn close, which is why we got the value we did. And so to describe the relationship, we say a very strong positive linear correlation. Now, again, this is just kind of one example to show you the math in action. We can actually do this pretty darn easily on the calculator, okay? So before we get into the next example, let me show you how to do this on the calculator. It's actually quite simple. I'll bring up my TI here. And basically what I'm going to go in and do is go into stat, and I'm going to edit. I'm going to put X values in list 1. And I'm going to go ahead and put the Y values in list 2. Okay? And if you want to look at the scatter plot, you can. You can go second, stat plot, turn your plot on. And then you're going to highlight the first one, which is scatter plot. X list is list 1, Y list is list 2. And then you're going to do a zoom 9 to look at the graph. And there's the scatter plot. We can see it. It basically looks like ours, almost a perfect straight line. Okay? But now what we can also do is we can compute the value of R. So to do that, we go stat calc, And we're actually going to go down to number 4, linear regression. AX plus B. This is going to give us some information. This actually represents the equation of a line where A is the slope, B is the intercept. We'll actually talk more about this in the next lesson. But for now, I'm going to hit that. And by default, it should pick up this 1 and 2. Okay, oh, and there we go. And what my calculator should be showing me is the R value, and it's not. So if yours is not as well, we have to go in and turn our diagnostics on. This should only have to do once. So to do that, you're going to go second 0. This is going to bring it to a catalog of functions the calculator has. It's alphabetical. You're going to go down to diagnostics on. Okay, you're going to hit enter a couple times. Once, twice, it should say done. Now go stack calc, do that linear regression. And not only does it give you the line of best fit, as we call it, that's next lesson, but it gives us R squared and R. R is the topic of today's lesson. Now look at this R value. If we round it to the nearest hundredth, this indeed rounds up to 1, which is what we got. It's not a perfect straight line. Look at the R value. It's so close to positive 1, but just not quite, because it's just not quite a perfect straight line. Okay, again, by hand, very close to the nearest hundredth, and there it is on the calculator. So let's do one more on the calculator. So you get a sense of how this works. X here equals the number of miles driven. Y equals the gallons of gas in the tank. And to sketch the scatter plot, I'm fine with doing it on the calculator. So I'm going to go into stat, and I'm going to clean up these. I'll go to the top and hit clear, clear, and now let me drop in these values. So miles driven, after 0 miles driven, we had 20 gallons of gas. After 30 miles, 18 gallons. The more miles we drive, the less gas we have in our tank. That makes sense. So there's miles driven. Here's the amount of fuel remaining. We had 20 gallons to begin. Now we're down to 18, 16, so on and so forth. Okay, so our data's in there. If I want now, I can go scatter plot. Make sure, again, it's on. It should still be on. Zoom 9. There's the scatter plot. So again, to look, as the miles driven goes up, the amount of gas left goes down. Does a pretty good job of forming a line, although not a perfectly straight line. I would intuitively expect an R value close to -1. It does a pretty good job of forming a straight line with a negative slope. Well, let's figure it out quickly. So we'll calc the linear regression. And what do we get for our R value here? The R value is approximately -0.9961 to 4 places. And so here we have a very strong negative linear correlation between the two variables. Okay, they're very much related, as one may expect. If I did a scatter plot where I took your height versus your high school average, I probably have dots all over the place, because your height and your grades probably have very little to do with one another. Okay, but this is just the basics with correlation. We look at a scatter plot, we compute the value of R, we interpret that value based on this number line, and we go from there. And there's all sorts of other stuff we're going to do. Next lesson we'll be coming up with the equation of the line of best fit, and then the third lesson deals with other things we investigate to really get a sense of how well the variables are related. Okay, folks, but I hope this wasn't too bad. If you have any questions, please reach out, and we'll get the next lesson going up soon. All right, have a great day.